group from the Sustainable Energy Network, and I'm going to pass the mic to them for a little while, and then we'll get on with programming.
Hi, my name is Eric Crone. I'm a junior chemical engineer here at UNR, and I joined the Sustainable Energy Network last semester. We're a group that's focused on getting students associated with energy like companies and professors to be able to either get internships or research opportunities. We also we're working on a few projects as well, ones that make both our campus or just our campus more sustainable, either in energy or even recycling, just a little more green. We've done a few, we're sponsored, so we actually have gone on a few trips. We got to go to a conference in Vegas last spring, and the main thing we're here is there's a meeting tonight at 6 p.m. in the physics building, room 300. If you don't know, it's right next to Schulich Lecture Hall. I feel like almost everyone in here should have at least one classroom in there, or one class in there. It's right next to the chemistry building. Our main focus tonight is just to plan our projects for the upcoming year. So if you're interested in getting involved in that, I would highly recommend you show up to this one, because then we're going to form our committees, form our what we want to do for the upcoming year. What else we? I mean, that's pretty much it. Just show up if you're interested, even if you're not entirely sure. We can answer any questions. Are there any questions right now? The meeting should be about an hour. I mean, it really depends. I think we're forming committees, and we might let them kind of go into their own meetings. And if that happens, it kind of would depend on the group. But if you have to leave or you have other plans, then just show up as long as you can, and we'll catch you up or throw you on the email list and catch you up later. Any other questions? All right. Thank you for your time.
Okay, on with some reminders. First off, good job on checkpoint 1. I hope you guys are all caught up on that. If you, by chance, have a dash or a 0 by your name in the gradebook for checkpoint 1, that means you need to come back and redo your checkpoint. So most likely that means you need to come back with new lifting fans chosen, and you need to bring your diagram with you. You need to have that graph. Those are the most important things. You can't just rely on the stats of DigiKey. So we'll get to that in a minute here. But also, fuel cell and battery learning module is due today, so please take that quiz. I believe you have till 11:59 p.m. Same goes with your CATME survey. You have till tonight to do that, so when you leave class, I would suggest you get caught up on those two things if you're not already. Your graded design concept reports will be in your box as they are graded. The graders are working on them, and you should have them sooner than later. But keep a lookout for that. They'll have comments on there about your design process and ideas, and then your general writing style and all that good stuff. At the end of the semester, you will write a second report that is largely going to be that one remodeled a little bit, as in it'll go to past tense and get updated. But you want to really take a look at their comments and maybe make those changes sooner than later, so that way you know what they're looking for in the future and you can start thinking about it. Checkpoint 2 is coming up also. That you have 2 weeks to do. So you must complete it before your oral presentation. And I'll get to checkpoint 2 in a minute, but you basically have to complete it in your next 2 skills labs. So you go and see your TA. It's not a big line, which is nice. And then your presentations are next week. Okay? Those are in Skills Lab. You'll present your project to your lab group. They're worth 50 points. Okay? That's quite significant. So please don't blow that off. Make sure you practice, practice, practice. If you've been to lab this week, you'll find, or I guess starting tomorrow, you guys are going to talk about public speaking in lab and how to put together a presentation. Presentation skills are very, very, very important. You will present something in pretty much every engineering class you have at UNR. And as you move forward and look for a job and all those things, presentation skills are really good to have. It's nice to be comfortable talking to a group. So when you go to, say, an interview and you have to meet with 10 people, then you're not nervous off the bat because at least you've had some experience. So pay attention to that coming up. Checkpoint 2, you need your parts list and cost. So basically an updated bill of materials. You need a copy of your receipts. So every purchase, okay, including fans, batteries, deck, skirt, all that stuff. Your deck material, bring in your material, okay, or your receipt, but to prove that you have it. It's worth 20 points for this checkpoint. Okay. I realize that it's pretty close coming up because your checkpoint or your skills lab might be tomorrow. So we're giving you an extra week since it just got posted, but I highly, highly recommend that you go out and buy your fans and batteries if you haven't already. There are 500 of you, in 1 second, buying fans and batteries. There's other universities doing this project and colleges and whatnot. Don't wait till last minute because you guys have probably discovered the DigiKey can be a bit frustrating and you finally find the perfect fan, and if you then go back next week and that's sold out, you are back to the drawing board. So please make sure you order that sooner than later, but you do have the next 2 skills labs to complete it. Question over there. Yes, do you have to buy all your parts by checkpoint number 2? Yes. So the idea is that checkpoint 3 comes up very rapidly, and checkpoint 3 you need to be up and hovering. So in order to do that, you need to have parts to build with. So we tried before not requiring receipts, but then we found that the night before checkpoint 3, everyone's down at Sandy's Electronics trying to buy them out and everything else. And so this helps you not procrastinate. So yes, you need to have everything purchased, have all your receipts. Right? The grade sheet is on Web Campus. Please take a look at that. If you guys haven't noticed, there's rubrics for everything in this class. And the best way to get a good grade is to make sure that you've addressed every category. Yeah? Yes, what if we still need to buy more points or parts, after checkpoint 2? You can still buy things, but go through the rubric and make sure that you have receipts for everything that we're requiring. So we're requiring you have receipts for the big purchase items and the things that are going to get you up and hovering. If you decide that you need a roll of duct tape or you need some spray paint or whatever, that's fine. You can buy that later. But we want to see those main components. So again, look at the rubric and make sure that you have addressed every line of it. Question? No? Anybody else? No? Who's purchased their fans? Show of hands, some of you guys? Okay. The other thing is, there are students' fans and batteries from last year in the EDL for sale. They are going quickly. A lot of them have their fan curves on them so you can look at them. They will save you a lot of money. Typically, people are selling stuff at about half price. So I'm sure everyone likes to keep some money in their pocket. I highly recommend you go over there and check out the table and see what's there. If you have something on layaway, that will be canceled this Friday. So if you put stuff on layaway last week, make sure you get over there and pay your money and pick up your parts. Yeah?
When you say layaway, does
Yeah, when we said layaway, that was you called dibs.
Okay.
So if you have your name on a sticky over there, I would suggest going over there sooner than later before some evil person switches the sticky on you or something like that. Okay? Not that anyone would do that in here, I'm sure. So if you do need to, going back to checkpoint 1, a lot of people didn't realize when they chose their lift fans that data curve was very, very important. People just looked at the rating and said, oh, it gets the CFM I want and the pressure, but they didn't realize that pressure is directly related to CFM. So if you are in that boat and you have to come back with new lifting fans, make sure that you bring your data curve with you. Okay? Have it ready to go so that the TA or myself or Dr. Lacombe, whoever's there, can check it off and make sure that you've chosen the correct fan. So fan curves. On the y-axis, you have static pressure. Okay? That's in your inches of water. Along the x-axis, you have airflow and CFM. Pressure is dependent on airflow and vice versa. Okay? So we've gone over this a few times. We had a clicker question, but I don't think it quite worked. If you go up, if you need, say, 0.5 inches of water, you go up to that pressure and go over and pick a curve. So if we pick the outside curve, this H fan, and I come to here, I can only get a half a CFM. Even though maybe the data sheet said, the main thing, the summary sheet said that I get 100 CFM. Okay? It depends on how much pressure you want. So what you probably want to do is you want to go search for a fan that's on the high end of the CFM you need and the high end of the pressure. Okay? I would check pressure first because that's what's required to get off the ground. So make sure when you choose your fans, you choose wisely and you use the curve. If you don't have the curve, then it's probably not the correct fan. So going on here, here's another fan curve. You notice there's 1, 2, 3, 4, 5, 6, 7 fans. 7 different curves on here. So again, when you go to order, be very careful that you're ordering, say, B70 and not B10. Okay? It's not that obvious on DigiKey, and it can cause some problems for you. Okay? So pressure matters. Pressure is dependent on CFM and vice versa, and the fan data curve matters. So please make sure that you have this data curve and use it. You will need that on your final exam. You need to know how to read these and what they mean. Does anyone have questions regarding fan curves? Everyone's straight now? Okay. All right, so last week we started talking about structured programming. I'm going to continue on with that. Lots of clicker questions today to make up for last week, and then we'll move forward. So, question? He asked, does everyone have to go to the EDL for checkpoint 1? If your group had a problem with checkpoint 1, I lured him back with clicker questions. Look at that. If your group had a problem with checkpoint 1, only one person needs to go back. Okay? Just one person in the group can go and take one for the team and be nice. All right. Anybody else? Questions about that? Make sure you take care of that. You should not be ordering anything until you get checked off by the TA. We don't want you to waste money shipping things back and forth and all that good stuff. Okay? All right, so structured program. Last week we talked about why we program and what is a program and having states and taking steps and responding to and changing states. Today we're going to move on with repeating certain actions, okay, decomposing programs and problems, and then solving them. And we're going to start looking at the code that you guys are going to be using to program your hovercraft. So I've got little snippets in here. You guys will have a skills lab, I believe, in 2 weeks where you guys program in class and you get a much better idea. So this is an overview for you so you can start thinking about how you want to program your hovercraft. So first clicker question number 1. This is when I figure out my clickers were not working last week. An algorithm might best be described as which of the following? A cookbook recipe, fully refined computer software, a large structure, a generic version of a program, or a clear desktop. Ready, go. Get in your answers quick if you need to. You got 5 seconds. Last minute. 10 people got in there. Good. Okay. Good. 93% of you. An algorithm is closest to a cookbook recipe. Review from last week. Okay. There we go. All right. Responding to and changing states. This is a little bit of a review. We were talking about last week, you have sensors on your hovercraft, and you're using them to try and sense where you are or some condition. And when you know that, then you want to change states. Maybe you want to switch from going forward to going backwards or whatever it is. So this is an example using Labview. That's the program we're going to use in class. And we're going to use Labview. This code is used to change states for a changing light condition. So if you were using light sensors on your hovercraft, you could have a program that looks something like this. The first icon here, program left to right, the first icon has a little picture of a Lego motor on it and the green side says forward. Okay? And port A, your NXT has 3 ports for outputs. It's got ports A, B, and C. So those are 3 ports that you can control outputs and basically send signals to relays or run motors or whatever you're going to do. Lego motors, that is, not servos. All right, so when you send this signal or put in this icon, basically this is closing your relay. So when you close your relay, that means that you're closing that trap door. Remember, a relay is an electrical switch. So it's closing that door, and that's allowing your electrons to flow. So when your relay gets closed, that is going to power something else, hopefully. Okay? That's the idea anyways. So you're throwing the relay off of port A, whatever's connected to port A, and also whatever's connected to port B. And then you see the signal, and it says darker, and it's got port 1. The NXT has 4 ports on it, 1, 2, 3, and 4. And that's where you can plug in your sensors. So you have light sensors, distance sensors, touch sensors, temperature sensors, all sorts of things. So here I'm saying, wait until light sensor 1 gets darker. And I've got a down arrow here, and I'm in port 1. And so I'm waiting for dark. So if you'll recall, the hovercraft board, or your track, is white, and then the end is black. So here I've closed my relays, which means that theoretically my lifting fans are on, and I'm propelling myself forward. I wait until dark, and then I get to this next icon. And this one has a motor, and it's got a stop sign. So basically, this is like applying the brakes. At this point now, I have opened my relay. When I open the relay, then that stops the electron flow, which means that I'll stop propulsion or stop lift or however you set up your hovercraft. And then the last thing over here is that I'm waiting for a certain amount of time. You see a 1, maybe you can see it, I'm not sure how big it is to you guys, but this says 1, so we're waiting for 1 second. So I'm going forward, I'm waiting for dark, and then I'm stopping something, and then waiting for 1 second. So I will encourage you to start thinking about exactly what do you want your hovercraft to do. I had a lot of conversations. It was really nice to meet a lot of you guys last week, finally. Place some faces and names together and all that good stuff. And we were talking about propulsion. It's like, how exactly do you propose this is going to happen? And a lot of you guys had a really clear, defined idea. Some people are still trying to figure it out, which is absolutely fine. You've got a couple weeks to worry about propulsion. But I will encourage you now to start thinking about what exactly do you want your hovercraft to do? What steps do you need to take to get down to the board and back? Because you're going to have to turn it into a programming code in Labview. So it helps if you start thinking about it early. One thing to note on here, these first 2 icons, if they have green here, you could be going forward or back. It doesn't matter, but these are both closing a relay if you had a backwards there. It closes a relay. Whenever the relay is closed, your fans are getting power or however you're set up. The only time that you open the relay is if you have this thing here where it says brake and you've got this red stop sign with the X in it. Your NXT is not capable of telling your fans to go backwards. So if this motor was a go backwards, it would say backwards here. And I've got an example in a little bit. That is not going to make your fans go backwards. All it is doing is just telling your relay to stay open. Okay? So that's something to think about. Questions? All right, moving forward then. So here we have basically the same bit of code here. The Labview program, again, right here, it waits until a light sensor perceives a darkening condition. And that's this part. Okay? So maybe you're in the turnaround zone. You've gotten to the end. And then this last part is where you turn around, or maybe you turn left. So here you've got ports A and B on. Okay? And then here you've got port A is stopped, but B is still on because you never turn that off. And so depending on how you set up, you could still be turning, right? If you had one wheel stopped and the other one going, or one leg stopped, you could do a funny dance and you go in a circle, like that. Like, come on, guys, it's Monday. That's funny. All right. I guess not. Sorry. Ha, ha, ha. Bad jokes for the day. All right. So what happens now, though? I've gotten to the end, and I need to repeat this program, but how am I going to do that? Do I just keep telling it what to do? But then it can't actually react to conditions. Right? I do a loop. Thank you. Do a loop. All right. So program repetition, which is also called iterating or looping, my computer science people, is another way that states can be maintained or modified as needed to solve a problem or create a solution. So in Labview, you have this big box here, and you see down here it's got iterations. You could say how many times you want your program to iterate or repeat itself, is all it is. And then you have a stop, and you can stop when a condition is true or false. And there's lots of ways to set up these loops. You can set them up to loop forever. You can set up to loop while the light sensor reads something, or your distance sensor reads something, or a number of times. Lots and lots of options. And again, you guys will get lots of experience programming in Skills Lab. So I don't expect you to remember everything today, but I want to give you an overview of the thing, so you can start thinking about how you're going to do this. Okay? So program repetition is called iterating or looping. Probably hear looping the most. Iterating in math, looping in computer science. So again, you would just put the rest of your program in this box, and whatever's in this box is going to repeat. Kind of nice. All right, so let's think about this in terms of algorithms. We talked about algorithms last week and cookbook recipes and all that stuff. Consider the algorithm, okay, if you wanted to, or if you needed to find a positive integer square root. So I've given you guys a really easy one. I'm pretty sure most people know the square root of 9 is 3, right? 3 times 3 is 9. So the reason I'm going through this is because this is kind of what you need to do. You need to think about the end result of your hovercraft. Where do you want it to go, and where do you want it to end up? And then start thinking about how are you going to make that happen. So if I said, let's write an algorithm to find the square root of 9, and you don't have a calculator with you, you have to actually do this in your head. Okay. The first step would be to realize that the square root must be between 0 and the given number. So my square root of 9 has to be between 0 and 9, because we know we multiply two numbers, the same number, together to get to 9. Okay. So then I'm going to let the initial guess be the middle number, because that just is an easy thing to do. 9 divided by 2 is 4.5. Okay. So that's my initial guess. Then I'm going to square that number. So what's 4.5 squared? Is it greater than 9? Yeah. I mean, it's at least over 16, right? 4 times 4 is 16. So I'll encourage you. I know we all love our calculators and our iPhones and all that, but I will encourage you guys to start thinking about math in your head a little bit if you don't already. Because sometimes you type in something funny to your calculator and you don't even realize it, and you can end up with an outrageous answer that makes 0 sense, and then you write it down on your paper and you get a bad grade. So start thinking about things in your head a little bit, and it'll help you make sense of things. Anyway, so if I square that, okay, if I square 4.5, that's going to be over 16, probably 18 or so, which is greater than 9. So that means that my square root must be between 0 and that middle number, between 0 and 4.5. And we know, because this is a simple example, the square root of 9 is 3. So yes, our number is between 0 and 4.5. If I had squared my number and it was lower than the original number, so maybe it came out to be, I don't know, 8 or something, then the square root must be between the middle number and the number itself. So if I came up with 8, the number would have to be between 8 and 9. Then you have to repeat this until you get closer and closer and closer, what we call iterate. Anyone taking computer science yet? Any older students? Yeah. Okay. So you put in your initial guess, and then you let the computer loop through and loop through and loop through and come up, and it will converge on an answer. Hopefully, well, it'll converge on 3 in this case. But it will keep guessing and guessing and guessing until it gets closer and closer to the answer, until it gets the same number twice. Okay. So these are steps in an algorithm in order to find the square root of a number. You guys need to look at your end result for your hovercraft, what you would like it to do, and start thinking about, break down in super obvious steps, like I've done here, to find a square root, over how you're going to program your hovercraft. How do you intend to get to the end? What motors need to be running? What fans need to be on? What light sensors need to be working? Think about all those things. Okay? So let's look at these steps in a flowchart. Flowchart was created using this free software called Raptor. You guys can get it. I'll give you the website on the next slide. And it has the ability to graphically show the applied algorithm. So this flowchart is just the steps that I just went through in text. Very exciting stuff here, right? You start. That's my favorite. I can do that. Okay. You get the input. So you put in your value. Okay. And then you see loop. Anything between the loop up here and the end loop, which ends down here, you see this number, is going to repeat over and over and over again. And those steps in the algorithm are where you take that middle number and you square it, and you see if it's higher or lower than your original number. And you go through and you answer all these questions. Is it yes, no? It's like one of those quizzes in a crappy women's magazine. Does he like you or not? Really? Okay. The guys are like, no, thank you. And then you loop back around. And the end output, once that answer converges, okay, then you end up down here and it spits out the answer. So there's lots of ways to represent these algorithms. You can start by writing your steps. Okay? You can make a flowchart. I would suggest you do this. And then you can write it in Labview. And then you can test it all you want. So if you want to look up this software and you want it, you can use it. It's called Raptor, Rapid Algorithmic Prototyping Tool for Ordered Reasoning Software. I'm glad they came up with the name Raptor, because that's a lot of a mouthful. It's available at raptor.martincarlisle.com if anyone wants to use it. You guys know these lectures are posted for you, so you can find this website later. Basically, it utilizes flowcharts to graphically represent the flow or path of a program. Okay? Flowcharts become really useful for you when you're planning projects and when you're trying to figure out math equations, things like that. Sometimes they're called process maps, which are for specifying actions. Okay? Maybe you'd have a process map for your group for what to do if someone is not helping you out significantly. Also, there's block diagrams, and those are usually used to show structural design. So you might hear flowcharts referred to as different things. All right, so basically the bottom line is these tools are very helpful for creating, analyzing, and explaining program or design operations. You'll become very familiar with them when you get out into the real world and get a job. All right, so in Labview, we're back to Labview here. Consider the following program that enables the hovercraft to stop when it senses the end of the white area, and otherwise it continues forward. Okay? So here you have, oopsies, sorry. Here you have, again, port A, forward. So that means that you have closed the relay connected to port A. Port C, forward, so you've closed that relay also. Remember, when you close the relay, that allows the electrons to flow, so you're powering something. Here I'm waiting for dark. Okay? Wait until the light sensor gets below 30%. And then I'm braking, A and C. This turns both relays off, or it opens them. Okay? So this hovercraft maybe went down to the end of the board and stopped. Okay? It saw the black, and it's like, oh, stop, I'm almost at the end. Again, you guys are going to be using Labview, so start thinking about it. You got some clicker Labview questions coming, so be warned. All right. See if you can explain the following, what the following program accomplishes. Notice that the paths can be extended to another line as needed for clarity. Okay. Programs always are going to read, in this class, they read left to right, okay, and you follow this line. So when you get to the end here, just follow it around and go here. Okay, so this one, we've got port A going forward, port C forward, so that means that your relays are closed. Okay. On port 1, my light sensor connected to port 1 of my NXT, that's waiting for darker. And when that happens, when that condition is reached, my light sensor sees black, then I've got a break on port A. Okay. So that means that relay opens and ceases to power whatever it's powering. Same with port C, it's a break. And then I'm waiting. Okay? I've got a 1 here, so I'm waiting for some time. And then I turn back on port A and port C. And then I wait for 70 milliseconds. It's got an M in front of there, 70 milliseconds, so 0.7 seconds. So, and you'll notice that I'm in this box and it says loop forever. Okay? So this is going to repeat over and over and over again. I'm going to keep going through these steps. So I go through this top line, follow this around. I get to my wait 70 milliseconds, and then I go back up. And I repeat again and again and again. So the only way to open up relays is to use these brakes or the stop when you see the red stop sign. Otherwise, they are closed and running. Questions about that? Yes? Can you repeat your question? Yeah. Yep. He said there's a black line in the middle of the track, so once the sensors pick that up, we can't use it. This all goes back to your choice of algorithm, how you want to do it. You could use it to follow it. You could put your sensors out wide enough and hope you don't get any drift. It's all dependent on how you build your hovercraft and how you program it. So that's why I would encourage you, is I'm talking about this program and showing you the various things it's capable of, is start thinking about your own design and how you're going to make this work. Everyone's program will be a little bit different. All right, anybody else? Questions? All right, it's clicker time. All right, what would the following program do? You've got 3 choices. You can, 1, close relay A, forward for 6 seconds, reverse for 2 seconds, and open relay A. You can, 2, close relay A for 8 seconds, then open relay A. Or you can, 3, close relay A for 6 seconds, and then open relay A. I'm going to give you a minute to read it before I start your 30 seconds. All right. Ready and go. Uh-oh, this is going to be difficult. Maybe. I'm going to add 10 seconds here so you guys have a little bit more time. Get in your responses, 5 seconds. Take a guess if you need to. Let's see here. So I've got relay A forward for seconds, reverse, relay, let's see. The correct answer is option 2. 23% of you, nice work. The nuance here is this. All you can affect, remember I said you can't make the fan blades go forward or back? All you can affect here with this is you can flip the magnet essentially, or shut the door, or whatever you want to call it. But all you can do is flip the switch. So anytime you have this green forward or green backward, all it means is that your relay is closed, which means you're powering something. So there's no way to tell if you're going forward or backwards from this code. Okay? That's up to you and how you built your hovercraft. So here I've got forward, and I wait for 6 seconds, so there's my first 6 seconds. Back doesn't do anything. My relay remains closed, so I stay closed for 2 more seconds, so there's my 8 seconds. And then, remember I said this is the only time your relay ever opens is when you have the one that's got the red block and it says break. Okay? So if you said close your relay A for 8 seconds and open relay A, good job. Nice work. If not, you'll get the next one. All right, questions? It'll be more fun when you guys get to program robots and see this happen, but for now. Okay, so I was telling you guys that you can use an infinite loop, which means that things repeat forever. Other loop types can be programmed. Down here, if I was going to program in this box here, and I've got iterations, this and this 10 up here, this means whatever's in this box will repeat 10 times. We don't always want an infinite loop, especially not in traditional programming. Infinite loops are disastrous, you'll find. But here, okay, you can go for 10 times. And so these are the various menus you go to get there. And again, you guys are going to work on this in class, so I'm not going to discuss it too much. But you have options, and we'll get to one other option on loops here in a second. Okay? So whatever's in the loop, it's going to loop through, say, 10 times. Okay? You got to follow it and look, how long will that run? And then if that loops, that can be nested in another loop. There's lots of different things you can do. Okay? So this is a for loop. Loop for 10 times. Sometimes you'll see do whiles or things like that. And that's loop while the light sensor reads black. Or loop while my distance sensor says this. And I'll show you guys an example. But here we go, next clicker question. So pay careful attention here. Approximately how long will the following program run? Okay. I've got a 1 second in here, and then I've got loops. How long is this going to run? I will start the clicker now. Ready, go. Two seconds, 1 second. 93% of you said, who didn't get in? I got 4 people who didn't make it. 10 seconds, good. That is correct. So what happens here is I'm running for 1 second, but I repeat 5 times. So 5 times 1 is 5. And then I come out and I repeat that loop again because it goes through here twice. So 5 plus 5 is 10. You'll start to see loops nesting into each other, different conditions, and again, you'll get practice at this. It's a lot more fun when you have robots to play with and hovercrafts. All right. Next up. Okay, repeating certain conditions. So this is another loop. Okay? And this loop repeats while the ultrasonic sensor at port 3 is less than 25 centimeters. So I'm saying repeat whatever's in this box until I am basically less than 25 centimeters. And when that happens, then you jump out of the loop and continue on with your program. So you might loop while the light sensors read light. I don't know. There are so many things you guys can try. Okay? This is just encouragement to start thinking about your hovercraft. So there's several other loops that will repeat on other conditions or states. You can use temperature, times, values, camera sensors, right? Any sensor you can plug into the NXT essentially. Okay, so lots and lots of options here. All right, an important quote. The sooner you start to code, the longer the program will take. That sounds really counterintuitive because usually we say start early. The point is you want to start thinking about your code and writing down your steps on paper. If you just pick up and start using Labview, you're like, I got it. I know exactly what my hovercraft's going to do. Chances are your hovercraft will do exactly what you programmed it to do. But what you think you've programmed it to do or what you think it's supposed to do, it's totally different. So I will encourage you to do some planning before you ever sit down at a computer and start writing code. It will save you a lot of time in the long run. For non-trivial problems, okay, tough things, you must identify and specify the solution, usually in the form of an algorithm, and then you develop a program. So again, you guys identify your solution. How do you get to the end and back without hitting walls or anything like that? Write down those steps in an algorithm and then go to the computer and use Labview. Okay, this goes for everything. Building highways, designing circuits, testing pumps, writing code. It goes for everything. It's easier to do a quick map, figure out what you need to do and what the end solution is before you try and make your computer replicate that. So decomposing a problem or solution, an effective engineer will implement large-scale designs by working with large-scale components first and then breaking them into smaller and smaller problems. Okay? If you are building a skyscraper, you don't just throw up the whole building at once, right? You consider the building's electrical and the plumbing and the walls and the windows and all those things, and then you break those problems down into smaller components and start hiring out people. So this is called top-down design, or top-down approach, okay? And you're basically decomposing a problem. So when we came in here the first day of class, we didn't just say, hey, build a hovercraft and we'll see you in December. See how that goes, right? We've broken down this hovercraft problem for you into smaller components, lift and propulsion and energy and programming, all these sort of things. Okay? This is also just good engineering practice, right? You can't just start huge. You got to break things into smaller problems that are actually solvable. It's very overwhelming to look at a huge problem and just try and do it all at once. So to do this, top-down design and development uses block structure for physical designs, and it uses flowcharts or process maps for working systems. So once your solution has been designed or developed at a high level, the details can be worked out. Okay? But you got to plan first. I guess that's the take-home message of the day. All right, another very common term is called black boxing. You guys hear about black boxes when planes crash? And they say, we're searching for the black box on the bottom of the ocean. Okay? And it just is this box no one can see or touch or do anything. It just stores information. A black box is literally something you cannot see inside. Okay? The ones used in engineering are ones that take some action, but the engineer chooses not to know or not see what is inside. So something gets done, but you don't really know how that gets done. You just assume that it's taken care of and working well. Black boxing is an important part of large-scale design and development. You come up with your big design, you break it up into parts, and a lot of those parts you want to be black boxed. The NXT robotics functions in Labview, what we're going to use to program, okay, black boxes pretty much everything. Okay? You don't worry about what this means. You just know that when you drag that over to your programming space that it's going to close your relay. Like, great, thank you. Okay? But you see this, but you don't know what the components are inside, and that's okay. These are examples of black box icons, for instance. So I've got a couple take-home points for you, a couple slides. The application of structured programming will be an important part of your hovercraft assignment. Okay? You guys can't get away with doing this project without programming, so we will learn to program, and you'll use Labview throughout your time here at UNR, so it's super useful software. You'll probably use it when you get a job. Structured programming and top-down design will always be the most important part of your engineering designs. You can't start with the small things and build up. You got to have a plan first. Okay? Please remember that a program is just a series of steps to solve a problem. So we've talked a lot about what programs are and how they work. Okay? And essentially, it's a set of steps. So what steps do you need to get your hovercraft, again, to the end and back? If you take time to design your hovercraft programming solution, you're going to find it a lot easier. So remember, don't just sit down and start programming. Start thinking about it beforehand. It's going to make it a lot easier to diagnose problems, to modify your hovercraft, and to repair it. Everyone's going to have to do some troubleshooting on their hovercraft. I guarantee it. So this will help if you have it broken into, say, subsystems and you know the steps used to program. So next up, identify the tasks needed. Here's a sample hovercraft operation provided in high-level task statements. The hovercraft will move down the hallway. Check. The hovercraft will stop if someone is in the way. The hovercraft will turn right or left as needed at the end of the hallway. The hovercraft will stop when it's arrived at the professor's door. So if I said, I want a hovercraft to arrive at my door, you'd have to start breaking down the steps. How is that going to work out where it's not going to get trampled and it's not going to get lost or whatever else? Once you've identified all the actions that need to occur, you can break them down to solve the smaller, easier problems. So if your hovercraft needs to move down the hallway, that means you got to turn your motors on or close your relays. So start thinking about, again, write down the steps your hovercraft needs to complete, and then write down the physical steps. What motors need to come on? When does my propulsion need to activate? Okay. What batteries are powering what? What sensors am I using? Okay. Big, broad topics you guys can start discussing as a group. So never solve big problems. I'm not telling you to be lazy. I'm just saying with quality design, with a quality design development process, you should never have to. You always want to break things down into small, solvable problems. Same goes with all your classes and your homeworks and all that stuff. Put things in perspective. Have a great Monday night. We'll see you guys Wednesday.